I'm Evan Czaplicki. I designed the Elm programming language, and sort of over the course of thinking about functional reactive programming over the past couple of years, I've learned some things. So this talk is really distilling those years into like a 40-minute thing, so you don't have to go through the same thing that I did. And I went with controlling time and space because at the time I was feeling like some kind of time lord with like time travel, but the real focus is on understanding what FRP is, and there's quite a lot of diversity about what that term really means, and sort of diving into that and sort of being able to pick that apart. So our goals for today are to understand what is FRP, how do we categorize different things that sort of fall into that umbrella, and then how do we evaluate those different things in a nice way. So the way we're going to get started learning these things is start with sort of what I'm calling first order FRP. And this is kind of what Elm looks like, and then we'll branch out into a bunch of different variations that sort of build on that core. So first thing is first order FRP. So another way to think of that is like how it works in Elm. We'll see why it's first order in a bit. So the sort of key thing to think about is when we're dealing with FRP, what we really want to have is a way to deal with interaction from the world. So we have a user over here, and they're typing, and they're looking at things. And so we're getting sort of key presses, mouse events, and bringing that into some sort of processing system. So in Elm, this is called the signal graph. In JavaScript, it might be just a tangle of callbacks. So sort of what FRP is about is rather than using callbacks and these kind of ad hoc ways of structuring time, we actually have a system that gives it explicit structure that you can talk about in a more concise way. And then we process these things and send them back. So we say to the computer, hey, you should show this on screen, or you should send this HTTP request, or these various things. So we get this core of signal graphs. So the key part of a signal graph is that it has inputs from the world. So these are things like mouse.position. And if you look at the type of this, that colon means has type. And it's not just a pair of integers, but it's a signal of pairs of integers. So it's a mouse position that's changing over time. So as you move your mouse, that value is updating. Another example of this is keyboard.lastPress. So this is the last key that's been pressed down. And you can think of this the same way. Time is passing, and we're seeing the value change over time. So in this case, I was typing hello, strange loop, and then I got distracted, and then I surfed the web for a bit, and then I came back at a later point. So you're sort of seeing this change over time and having a way to talk about that explicitly. So from inputs, we can do a little bit. That's sort of like the raw information coming from the world. But on top of that, we want to be able to transform those things. So for that, we use this function lift. So we take in a signal. So we can take in our key presses signal. And then we have a function that goes from A's to B's. So we take the values of A, and we go make a signal of B's. So an example of this would be saying, we have this function is consonant. So we're checking each of these letters, true or false, if they're a consonant. And what we get out is a new signal where we say, OK, H, that's a consonant. E, that's not. L, so on and so forth. So we can actually transform these values as they're changing over time. And so here, what we're doing is we're really handling a time-varying thing rather than doing a more like event-based callback kind of system. The next thing we can deal with is state. So in Elm, this is called fold P. And you can read this as fold from the past. It's meant to look just like fold from the left, fold from the right. And what's going on here is, again, let's take our trusty key presses signal. And when we actually use fold P, we're going to give it a starting state. This is this guy. And a way to update that state. So whenever a key press comes in, I'm going to say, OK, cool, I got the key. I got the state that I'm working with. And I increment that by 1. So when we look at the signal that we get out, we count 1, 2, 3, 4, 5, so on and so forth. And so this is a very simple example of carrying state, but you can think of something quite a bit more complicated where perhaps you have a to-do list application and you want to model what your program is doing as things change over time. Finally, we have a way to merge signals together. So the very basic one is called merge, which it takes two signals and it just kind of merges them together. This is one of the well-named primitives. There's another one called lift2, questionably named primitive. This takes two signals, and at any point in time, it applies a function to both of them and produces a new signal. So this is a way of saying if I have a signal of x coordinates and a signal of y coordinates, I can apply a function that puts them together. And this becomes useful when, let's say you have window dimensions, mouse position, a whole bunch of signals. You can start to bring these together. And so in addition to lift2, there's like lift, lots of them, lift 3, 4, 5, 6, 7, 8. It stops at 8. But you can go higher through various tricks. So what we have is a way of talking about this graph, setting up an input from the world, transforming it, updating some state, merging things together. And this gives us the tools to build this kind of network, this signal graph. And so if you imagine a program like a to-do list, like this, you can think of this program as we model the inputs, we go update some state, we transform that into something to show on screen, and sort of we have this architecture for our application. So that's sort of the operational details. That's kind of what you would learn, the very abbreviated version of what you would learn if you dug into Elm. But it doesn't really get at the sort of principles that went into that design. So when you think about the core design, you start to see some details that aren't apparent immediately. So the first one is that signals are connected to the world. This is a key property of Elm system that doesn't appear everywhere else, but you have direct connection to mouse position or keyboard. Signals are infinite. This one is subtle, but it essentially means that there's no such thing as deleting a signal. There's no you can't have an input that you then later throw away. This is like saying, I have the mouse, but then I took the mouse off of my laptop. Like it doesn't, like essentially it's saying the inputs to your program are fixed. Another property is signal graphs are static. There's a known structure for your application from startup all the way into the future. And this sounds like, oh, maybe it could be dynamic. We'll get to that. There are tons of trade-offs that come with that. So this is actually a property that gives you lots and lots of power that we'll get into in a bit. Finally, it's synchronous by default. So what that means is when you type hello, as someone who's observing your application, like you want those letters to show up in that order. And so when you have branching structure like this, you need to be sure that those events flow through and maintain order. So in Elm, that's maintained by default. That property isn't shared by all variations. So, okay, what do we get? What do we get when we make these design choices? So the first one is efficiency. This one, it's not clear at this point why I'm saying this, but essentially what's happening is everything's event-driven, right? An event comes to the world, it flows through our graph, it may get sent back as an update. And with our stateful nodes, we need to look back at the previous state, and that's it. So we'll see why it's necessary to point out that efficiency is a property that we have. Another thing is architecture. So this is a Elm program that's kind of like the typical example of a MVC-style application. And this is just hooking up to the world. And so you can see it's actually using local storage. So if I reload this page, the changes propagate over because I'm saving it. Which is to say, interacting with the world becomes quite simple. Now, when we look at the structure of this application, it breaks up nicely into 4 parts, as every Elm program will. It breaks up into a model. So that's tiny. Is that better? Ish, better-ish? Okay. We just want an overview here. We don't need to see the details exactly, but we first have a model. So we just are saying, here's the state of my application. I have a list of tasks. What is a task? It's a thing with a description, whether it's completed, whether I'm editing. So we're explicitly modeling what our application means. And from there, we have update. How do I take that state and step it forward based on stuff people want to do? So maybe we want to add a task or delete a task. And finally, we have a view, which is how do I take the state of my application and turn it into HTML that I can show on screen? And what's nice here is we can make sort of reusable functions. So I can say, how do I show a task on screen? And then I can say map that over all of my visible tasks. So I can start to build up UI in a really nice declarative way with these pure functions. So that architecture, that structure, comes from the static signal graphs. They guide you towards writing your applications that way. I consider that a really big benefit. Another thing that you get is hot swapping. So you guys may have seen the Mario program from last year. If you didn't, it's a good way to learn Elm in that isn't only like 10 minutes. So notice I walked him over to the side of the screen. And I'm going to change gravity a little bit, and now jump him, and then change it again, and suddenly gravity is stronger. So we're able to change the behavior of the program while the program is running and sort of see those changes propagate automatically. So the final thing that we get, well, not the final thing, but like the other thing that I felt it necessary to share with you guys today is the time travel debugger. So you may have seen this online, but we've got a new version coming out that's easy to install. And so I just wanted to do a tiny demo of that. So here's that trusty Mario program. And we've got like Mega Mario. Ah, man, I changed the code by accident last night and forgot to change it back. But so we can see where Mega Mario was before. And we can pause this program and sort of go back in time to wherever we want to go. And so say we go like near the beginning, and we pick up where we started there. So we say, OK, I didn't want to walk to the left. I wanted to walk to the right. And so one cool thing here is that we can look at data in our program. So if I go back a little bit, you can see the arrow's value. I'm now pressing right. And if I go back a little more, I'm pressing up right now. And then I stop pressing up. So you can start to get really cool insights about what's going on at your program at particular points in time. And what's neat about this, you can, oh yeah, there's another thing that's neat about it that I forgot to tell you. OK, so you see him jumping around. OK, so here's the code. And again, it's got model, update, display, these parts. Oh, geez, what's going on here? OK, and I want to change, what do I want to change? I want to change gravity again. So when I save that, and this is in Sublime Text, those changes again propagate, but they propagate for the whole history. So we can see that now Mario's can jump like way too high. So we're like, that's no good. We want Super Mario to have like a reasonable kind of jump. OK, so now we've got Super Mario with good jumps. OK, so these are kind of like the core things that come from having a static signal graph. A lot of these abilities to swap encode and replay code comes from the fact that if we know what the program looks like at the start, we know what it's going to look like in an hour, in a day, and we don't have to do some kind of crazy complex analysis to figure that out or to match things up. So that's sort of an overview of what first-order FRP is like. But the question you may have in the back of your head, what happens if signal graphs could be reconfigured? What is higher-order FRP? Surely higher is better. So this is the question that sort of guides a lot of the thinking on FRP and a lot of the research, because it's a very, very surprisingly hard question. So there are a couple ways that it has been pursued. We're going to explore them one by one, and they sort of fall into sort of nice separate categories. So let's dive in. So the first one is higher order FRP. So this is really just saying, OK, we took this core design, and we don't like that signal graphs are static. We want to get rid of that constraint. So what do we need to add? What do we lose? So one thing I should point out is that with all of these variations, it's not better or worse. It's trades, right? Whenever you're making this decision, it's like, I'm going to get this feature, and I'm going to lose this other one. So what happens when we get rid of this core design that signal graphs are static? So typically, this is with a function called join. So not super clear exactly what that might mean, but here we have a signal of signals. Again, it's not super clear what that might mean. But you can think of it as, I have a group of signals, and I'm picking which one to listen to right now. So you can think of this signal as the guy coming out here, and this signal as like choosing one of these. So as I get updates, I listen to a different signal coming in. So that seems straightforward, right? It sounds plausible. So already at this point, we have some questions. So what happens to these signals that aren't in use right now? Right? No one's listening. So should it keep running? Should it pause? This is a surprisingly difficult question. Now, you get into even crazier issues when you start adding signals that hadn't previously been observed. And you can keep adding these and adding these. So to make this a bit more concrete, let's see an example where we see the bad behavior here. So here we have a very simple signal. It's counting mouse clicks. So I click, it increments. I click, it increments. And let's see something a little bit more complicated. So here, we've got something that's either counting mouse clicks or it's 0. So if I put true in, I'm going to get count mouse clicks. If I put false in, I'm going to get a constant signal of 0. So let's say we start with true, and I click 5 times. So I should be at 5. Now I go false, it's 0, and I click 5 more times. And I go true again. OK, what should the value be of my signal? Should it be 0, because I'm restarting? Should it be 5, because I'm picking off where I left off? Should it be 10, because that's the total number of clicks that have happened over the course of this application? Now, because a lot of this research happens in purely functional languages or languages where we want to have properties about equational reasoning, our answer is chosen for us. So if you look at this code, count mouse clicks, and this code, count mouse clicks, they're the same expression. So it should be possible to replace this variable with click count and have the same behavior. So essentially, our behavior is chosen for us. When we get to that point where we go true again, it needs to be at 10. It needs to be the count of the full number of clicks. So where this starts to get crazy is, let's say no one defined that, but they wrote this program. So I start my program. This signal is false, so it's 0, 0, 0, 0, 0. I wait 10 minutes. I wait 20 minutes. And I'm clicking away like a maniac. And then suddenly, I switch to count mouse clicks. This is a signal that's never existed before, but I know that it needs to keep track of all of those past clicks. So I'm in the place where I don't necessarily know that I'm going to need that signal. I know that it needs to use all past history. So I'm in a bad situation. Essentially, the problem is creating a new signal may need infinite lookback. I may need to look back at all the previous events to be able to reconstruct the signal so that I have these properties that I want. Another way to say this is memory growth is linear with time, right? So every click that happens, every time step that happens, I need to keep track of that in case you have to look back. The solution isn't that this is a bad idea. It's that we only should switch to signals that have safe amounts of history, right? It's not that switching is necessarily bad, but that particular kind of switching definitely causes problems. So what this has turned into is, how do we restrict the definition of join with fancier types? So how do we write a way to switch between things that rules out the possibility of this infinite look back so we can implement it efficiently? And this is where a lot of the research has gone on this topic. And when you see a modern library in Haskell or wherever else that is in this category of higher order FRP, it's going to be doing a trick like this. So one cool example of it is this paper, Higher Order Functional Reactive Programming in Bounded Space. The names get very long for these papers when your topic is functional reactive programming. So he takes a quite sophisticated approach where he uses a thing called linear types. And this is a kind of type system that doesn't appear in Haskell or Camel or Agda. Or I don't know if it appears in Coq. I heard it came out in Idris. The point is that like this is a rare type system to see in languages that you can go and try out. But he's able to show that you can't write a program that looks back unless you specifically say you want to save that information. So we can write programs like this, but we're making some trade-offs. So we got rid of the idea that signal graphs are static. So we're losing that hot swapping is really easy. We're losing that time travel debugging is straightforward. We're losing that architecture is really straightforward. And we may be dealing with a slightly more complex API or perhaps a more complex type system. So when thinking about this one, let's say there weren't any trade-offs here. Let's say this was like the problems were solved. let's look back at the architecture of this to-do MVC thing from before. So when I look at this code, and let's say I could switch on signals, would I want to architect my application that way? Like, given the ability, would I use it? And so maybe that would mean that instead of state that I model like this, it has the tasks isn't just a list of tasks, it's a list of signals of tasks, and we're doing some more complicated signal structure with that. And I'm not sure that's a better way. I think that's something that I'd like to see some examples, and that could be quite interesting, but I'm not totally sold yet. So next, we have a thing called asynchronous data flow. So if you know reactive extensions, reactive Coca, Bacon.js, essentially, if you see something that looks like FRP and it's in an imperative language, it's probably in this category of things. So again, we can look at our core design and see which things we cross off. So of course, we cross off that signal graphs are static because, yeah, we don't want that. We cross off that signals are infinite. So this is another way of saying that signals can end. Like I can start it up, it can trigger 4 events, and then it can die. Finally, we get rid of the design that it's synchronous by default. This doesn't mean you can't have synchrony, but you have to do it yourself. That it's asynchronous is a hint that that's one thing we're getting rid of. So these guys use something called flatten. It may look very familiar. When you're writing an imperative language, you get this extra ability of naming things in a way that is clear for people. So flattening signals of signals, it's quite intuitive to name it that way. But this is the same idea, and it ends up looking a little bit different because we've given up on more of these core design points. I shouldn't say given up. We've decided to shoot for a different point in the design space. So if we look back at that program from before, where we were like, OK, count mouse clicks needs to be equal to count mouse clicks, we get all these problems. OK, now we're in an imperative language, and no one ever said you were going to have that guarantee. So whenever you create one of these signals, you're creating a totally new one. And what that means is when I do clicks or 0, I start with true, I count 1, 2, 3, 4, 5, I go to false, so it's 0, and then I switch back to true, and I count 1, 2, 3, 4, 5. I start at 0 again. It's an entirely new signal. So we're creating new things, and there's some mechanism of cleaning up garbage as we go. We still have that question from before of what happens when no one's listening to a signal, right? You may have created a signal and no one's paying attention. So some variations of this style have a thing called hot and cold signals. So reactive extensions in particular has hot and cold signals, meaning if I have a signal and no one's listening, there's a joke here. If I have a signal and no one's listening, what should happen? And if it's hot, it's going to keep producing things, and if it's cold, it's going to stop. OK, so finally, we have arrowized FRP. So this is something you can see in Haskell with a couple libraries. Yampa is sort of the first one that came out. Netwire is a, I think, more modern version that looks quite interesting. Elm has a thing called automaton, which is the same concept. So when we look at this, again, we go to our core design. We cross off that signal graphs are static. The whole point of this is to try to get rid of that constraint. Now, in this one, we cross off that signal graphs are connected to the world. This is a very clever and interesting choice that has some cool effects. So we'll get into this by looking at how this library works in Elm. So for the basic API, we've got this function called pure. And this is creating an automaton. So you can think of an automaton as a little robot who takes things in and gives you things on the other side. So I can think of a pure automaton as that increments by 1. You give it 1, it gives you 2. You give it 42, it gives you 43. You give it 100, it gives you 101. I think I got this right. And so here is how we actually write that out, right? We have a function, it takes in an input, and it increments it by 1. Next, we have a way to model state. So this is quite like a fold P. This one's nicer to see by example. So with the state, we say, here I have my base value. So in my brain, I have 0. And then as my step function, whenever I get in a value, I'm going to say, cool, that's a nice value you gave me. And I'm going to take my total and increment it by 1. So someone gives me the string hello, and I say, oh, I got a thing, 1. And then I give out 1. And someone says, how are you? And I say, OK, 2. I got 2 messages. And so here we can model state in the same way. The last thing that I want to show as part of the basic API is how we chain these together. So when you have 2 little automatons who are processing information, you can put them next to each other. So this is saying I have one guy that takes A's and gives B's, one guy that takes B's and gives C's, and I can just put them next to each other. So if we wanted to say +2, we can just chain +1 and +1. So 1, 2, 2, 3, and process that information. So this gets interesting when you want to start switching on things. So you can think of each of these as a little automaton who has some state. And these are all counting. So their state starts at 0. And we're going to put them into our sort of active position. So values will be flowing through here. So if we start out, we know this guy's 0. And then we pass a couple events through. Let's say 5 events go through. So increments 1, 2, 3, 4, 5. Then we switch it out for the green one. Now, at this point, this guy's holding 5. This guy's holding 0. This guy's holding 0. What's really clever here is that these nodes aren't connected to the world. So when we take it out of the graph, this question of what happens, does it keep running, it's just answered. It doesn't keep running. It's not connected to anything. And what this means is we can switch things in a more creative way. So let's say I give this 3 events, 1, 2, 3, and then I switch again. So now I've got 5 in here, 3 in here, 0. And we can sort of switch this in really interesting ways. So this is kind of the key insight of arrowized FRP. But we gave up something really important, which is that we can talk about signals coming from the world. So in this system, there's no way to talk about mouse position. That's something that exists externally. So what that means is arrowized FRP is really about structuring code. And so it can show up in a library for Elm or Haskell or whatever. And it's in competition with like using pure functions and modules as a means of abstraction. So the question to ask yourself here is, for my particular domain, is this way of structuring code giving me benefits? And I know there's been success with music and with NetWire. There may be some other cool things of structuring your code. I personally haven't used it a lot, but it's compatible with all of these different approaches. So when we zoom out, you notice I put the circle around Elm to have all 3 colors, indicating that this isn't a competition of like which one's better, but rather different points in a design space that are complementary. So when we think of how this connects to Elm, how does higher order FRP connect? I mean, this is really adding a feature. This is something that could be done. I personally don't want to take that step and give up the properties that Elm is able to get. If we find a way to do it that's nice, that's totally possible to add to Elm. With asynchronous data flow, here you're giving up the synchronicity guarantee. So this isn't something you'd embed in Elm. It's something that you'd embed Elm in. So let's say you're Prezi, who employs me, and you're thinking of using Elm in your system. You'd like to make a little part of your application. What you can do is make that part in Elm and hook up to it with Bacon.js or RX or whatever, and have that interactivity. So you can have all these nice guarantees when you want, but still integrate with a system that has something more complex going on. Finally, arrowized FRP, it can just be a library. It is a library. And so when we think of the broad categories here, we can think of one as static graphs, graphs that don't change over time, and the other category as dynamic graphs, graphs that do change over time. And these are the sort of broad connecting categories. And then for distinguishing these bottom 3, you can look, are there infinite signals? Another way to tell this is like, is it in Haskell? It's probably in this category. Finite event streams. So this is signals that can end. An easier way to tell this is like, is it in an imperative language? And finally, neither. In this world, we don't explicitly talk about signals, or whether they're finite or infinite or not. So this kind of gives us our taxonomy, or like different points in the design space. So let's sort of try to pick out the lessons we can learn from this. So I know I sort of introduced parts of Elm really, really quickly. I didn't do a lot of examples. You can learn more at this site about Elm in particular. If you want to learn more about the history of FRP, specifically first-order FRP and higher-order FRP, this is my thesis, and it has a section on history of FRP. And if you look at the citations, you'll just see links to all the papers that had been published by the time this was written. When it comes to categorizing things, it means I'm running low on time. When it comes to categorizing, the questions you want to be asking are, is it synchronous by default, right? Am I getting these ordering guarantees where I know that if someone types hello and clicks a button, that we're going to get it in that order and not the button click happens halfway through because the processing it takes too long or something. Does it allow asynchrony? So it's not just that you want synchrony, like that's a nice default, but there are times when you don't want to block everything. So you need to make HTTP requests, you need to make writes to disk. And so Elm builds in this idea of asynchrony in a nice way, where you still get the default of synchrony, but when you don't want it, you can explicitly say. And not all systems that are out there have a plan for how asynchrony will work. So that's something that you should keep in mind, especially when you're looking at higher order FRP. Can I talk about inputs? So this is essentially a way of saying, like, is it a kind of arrowwise system? Is it a way of structuring code, or is it a way of talking about events? Can I reconfigure my graph? And when you want to evaluate this, the question isn't, how can I get the fanciest like words on my library? It's what properties do I need for my application, right? So when you're looking at something like reactive extensions, and you want to write some server code where I've got 10 people connecting to my server, they all want some information, there, asynchronous by default is great. Like, why should any of them block depending on the order that things came in? Or if you're dealing with some system where it's just not that important to have this synchronicity, that will fit you really well. If you want to have the kind of debugging tools that Elm has, you may want to make a different choice. Yeah, what is debugging like? This is a question I can't answer for the sort of dynamic graph ones as easily, but it's something to think about when you're starting out. Is like, this isn't just a cool thing to start with. You have to carry this through for the whole life of your application. And finally, does the code come out nice? So there may be something where you like it, and then once you write a lot of code, things start to feel more complicated than you thought, right? So this is particularly important when you're talking about the asynchronous data flow kind of things. You can get more features, but you're paying a complexity cost for that. And do you need that in your application? Is it something that you can live without to get some more simplicity? So that's sort of the space of functional reactive programming. Hopefully I've sort of given you some ways of sort of categorizing and picking them out and things to explore. If you're interested in learning more about FRP, if you learn Elm, then it's easy to go to these other ones and you learn these principles which you can use there. But yeah, so hopefully this has given you some insight. Thank you very much. So we've got some time for questions, I think. Yeah?
So regarding the join operation,
yes.
And the argument that you need to look back in time and have all possible values that have passed through the signal previously in order to maintain reference and transparency, is there a reason you don't just model signals as effectful streams and then be done with it and say that the values are ephemeral?
Yeah, so that's the switch of going to the sort of asynchronous data flow style. So the question was, why with the join operator in higher order FRP, why keep that constraint where count mouse clicks should be equal to count mouse clicks? Why not just say, hey, that's not how signals work? I can't say for sure if there are libraries that do that. This is a design choice you can make. You get different trade-offs doing that kind of thing. That would be more in the ballpark of the sort of reactive extensions Bacon.js style, though. Any other? OK, yes?
I'll let you have one too.
OK. Yeah.
So with pairwise FRP, when it does the switching,
Yeah.
is it doing that like once you've already, like if you're doing it in Elm and you wire it up to some actual signals, does it do the switching after everything is running? And if so, how does that kind of switching make that trade-off of when it starts getting the values and all that?
Yeah, so the question is, like, when do you hook up an arrowized FRP system, and what happens once you do hook it up? So typically, you'll define your arrowized FRP system and design that dynamism into it, and then hook it up, and those sort of flow through, and things will be switched in and out. When it's hooked up isn't such a huge deal in that you can give it values at any time, and it'll step forward its sort of world. So I'm not sure if this is answering your question very well, but
Each switch is like reified in some ways?
yeah. Yeah, so when you step an automaton forward, what you're really getting is the value it produces and the new automaton that you should run. So you sort of are like forking reality and say, here's one where I've stepped the world forward, and I still have that value I started with. Yes?
Yeah, so in terms of part of what we were trying to do with parallelized FRP, in your to-do MVC, you have separate state and updates and view. So how would you take, say, the editor for a single line of a task, or say the whole to-do list, and include it in another application?
Right. So the question is about how do you get a kind of modularity in an application like the to-do list. Is that fair?
Yep.
So I think that there are a couple ways, right? So one is to use the higher order style, something like arrowized FRP, one of these reconfigurable ones, to give you that kind of abstraction. You can wrap it in that way. My opinion is that this is something we should explore more. In Elm, what I'm advocating right now, is sticking with module system and functions. So if you want to modularize your tasks, you'd make a module that is all about tasks. What's the model of them? How do I update? How do I view them? And then I make a module that's all about the actual to-do list. What's the model? How do I update it? How do I view it? And I can keep doing this sort of like nesting architecture to get that kind of modularity. And it's not clear to me that one way is going to be superior to the other, and I think there hasn't been enough exploration to know, like, this is the right way, or even if there is a right way for all cases. Yeah. Yes?
Have you looked at Haskell's machines at all?
I haven't.
They do implement the join operator, and it works in a relatively elegant way. It's interesting.
OK, I'll take a look.
I'm curious as to what your thoughts were.
Yeah, I haven't seen it. Yes? Yeah, so that is terminology that I think is a bit confusing. So we talked about, oh, sorry, the question is, how does push versus pull fit into this taxonomy? So with the asynchronous data flow, we talked about hot and cold, sort of what happens when no one's listening. So what push and pull is about is, with Elm, it's event-driven, so meaning it's push. You push an update to it, and that propagates through. What pull means is someone at the bottom says, hey, I want to see something, and so that goes through your graph and pulls values in, sampling from whatever that time point is. The argument we've made in the work we've done on FRP is that a push system can model a pull one, in that when you get to the bottom of your program, one way to say it is I pull the values through. Another way to say it is I trigger a push through. And so I don't think there's as huge a difference between this as the distinction isn't as important as it sounds. Yes? Say it again?
How do you
Okay, so the question is about how do you deal with sort of like too much data to process through your graph, right? Is there a way to drop things? Or so in the domain of UI, you're dealing with human input, so you're not going to be getting in that situation very often. So a lot of these systems are prioritized towards use cases like that. And I think so essentially, the subtext here is like, what is the like pushback like mechanism? I think I'm not an expert on this particular question. There may be FRP systems that do it. Elm is primarily concerned with UI, so it's not the major focus. I've gone over time a little bit. Let's chat outside if you have questions. Thank you very much.